trying to kind of step on this idea a lot because I think this is really, really important. So I'm going to talk about leader elections for a moment here. One of the big problems with leader elections is you end up with this kind of struggle between the time cost of recovery with the detection interval. If recovery takes a very large amount of time, you don't want to detect a failure and spawn a failure if you're not sure that it's going to come back. Like if it took 10 hours to recover a database, you would probably be willing to wait for an hour of outage before taking that 10-hour recovery process. So even if it then came back, you still wouldn't be able to be back online. So it's just very sort of tricky in that if you choose too low, you're going to have more outage than necessary. You're going to be detecting outages and then taking the long recoveries. And if you choose too high, you're going to have more outage than necessary. And this is sort of very relevant to HBase because HBase does have an overly high recovery time. It's getting better, but certainly not in the seconds kind of range. So I drew this cool hand-drawn diagram because I couldn't figure out how to make graphs. How do you make a graph in a program? Like,
that's why you want to put the guys with sales.
Yeah, that's probably true. So we have a solid line, and that's sort of between the the very bottom we have. Okay, this is the average maximum garbage collection pause time you think you might have. Is it 1 second, 10, 20, 30, or even goes up higher? And that kind of informs your detection time. If you think your average max garbage collection pause is going to be around 10 seconds, you probably don't want to detect a failure that only lasts like 4 seconds. So you're going to wait. But you also have to pad it, which means that you end up with this big, thick danger zone of kind of, these are the times when you shouldn't detect recovery. So what this essentially means is that the longer your garbage collection cycle is, the longer you have to tune your detection time outwards. And this is essentially the basic reason why HBase ships with a 60 second, 120 second now, 120 second timeout. So by default, HBase will detect a failure and react to it only if the machine has been gone for 2 minutes. And that's a toughie for people who are trying to get stuff done on an interval that's less than 2 minutes, which is probably a lot of people. So leader elections is really important because it drives you into this kind of bad cost decision where there's really no great solution here. And there's a giant area of, if you set your detection time too low, you're going to be kicking off these expensive recovery processes that just take a very long amount of time. So combined with garbage collection, it's a real pain. So now we're going to kind of dive into like the details of Decomp. And one of the cool things about Decomp is that I can really talk about the internals of it because it's based on not only a public computer science paper, but the specific improvements that we made are, actually I hate to say the P word, but they are patented. So definitely this is one of the most sort of impressive computer science patents I've ever seen. And it's pretty cool. So the basic concept is you have a majority quorum, and there's a sort of a, should have put air quotes around, a fixed number of participants, and the essential idea is a majority of them must agree for there to be a change. So pretty, seems, majority election kind of thing. I put air quotes around fixed because over time we of course can grow the number of replicas and shrink the number of replicas within some bounds. So it's not like fixed eternally. Failed nodes, when they do fail, they become unavailable, unfortunately, but normal operation succeeds on all the other nodes as long as the majority quorum is still available. Recovery and self-healing happens when a node rejoins the system, comes back up, rejoins the system, checks its own log and data store, and then talks to the other members and essentially decides to catch up, and all the other nodes help them catch up on all the missing transactions they haven't seen. And I have a cool diagram of how this works. And in a disaster recovery place, a complete loss can be recovered by copying from another replica. In HBase, this is even easier because we store essentially the data inside HDFS, which itself is failure fault tolerant. In terms of HBase itself, though, this is kind of where we start departing quite radically and rapidly from normal HBase, stock HBase. So the big thing is that there's multiple replicas for every region, and clients can connect to any region. which is great. So clients can read from any region, so that can help spread your read load around. Read operations are also local, so they're as fast as they've always been. And write operations require coordination for every node to be aware of these writes, and so for data to become durable. So I'll take us through a cool little. Hold on a second. Wow. I messed with the PowerPoint settings and screwed up the Google graphic. So let's go with this one. All right, so again, majority quorum, we're going to see a fixed number of participants. In this case, we're going to go with 3. So there's 2 required out of any 3, so there we can tolerate a single failure. We can also run the system with more than 3 copies, 5 copies. And also in the case where you're running it across data centers, you might run 3 in one data center and 3 in another data center. So you end up with lots of extra copies to be tolerant of both remote and local failures and all this sort of stuff. So the majorities must sort of agree. So in this case, one of the nodes, hold on. Okay, in this case, we're going to see, so we have a transaction ID. Every time there's a new transaction, it's getting bumped up, and they all agree on it, and it becomes this global transaction ID. So everyone's sort of aware of the same thing. So in this case, A, B, and C are all agreeing that 170 becomes a new agreement, and things move forward. During failure, A will fail, but B and C can continue to agree on transaction IDs, 171, 2, 3. So the rest of the nodes can operate normally. So when the other node comes back, at first it sort of boots up into sort of safe mode and reaches out and talks to the rest of the people and finds out that they're actually missing a bunch of transactions. And the other replicas will send those to them. And we will see that it's going to replay 171, 172, 173. Now, having replayed the exact same series of transactions as the rest of the nodes, it's now caught up and getting marked as such. During a DR situation, you're going to see a node just completely die and be taken off the system. At that point, you only have 2 replicas, and they're, of course, not resilient to yet another failure. So we're going to add another node, in which case we usually replace the missing node. In this case, the complete loss is caught up from another replica. So this works by copying the state from one of the other replicas to the new node. Having received all the state, we can then realize it's fully caught up and rejoin the quorum. So as we're talking about more HBase, so part of the details of how this works is pretty cool, and that's all I've been thinking about for a couple months now. So I had to throw in some slides here. One of the big concepts here is that when you do an HBase operation like a put, you end up with an RPC call against one of the servers, one of the region servers. So what our code does is it intercepts these RPC calls. Then we inspect the call and decide whether or not this is a call that can be satisfied locally by just doing the logic, or whether or not it has to be coordinated. So for example, if we do a put that has to be coordinated, what we're going to do is we're going to ask Decomp to do this coordination. We're like, okay, we want to do this put, but can you please coordinate it with everyone else? Once we've heard back from a majority quorum of all the other nodes, we now have sort of agreement that everyone is not going to forget this node, and or this operation, and we can process it locally and tell the client, hey, that worked. In the meantime, everyone else is now also doing the same thing as well. So they're processing these new puts as they come in. So every single region server is sort of progressing forward simultaneously, and data is immediately available on all the nodes. So a couple things to note here is that there's no cross-machine locks, no single point of failure, no transaction coordinator, none of those things. And this is what sort of paxos and Decomp brings us. Brings us the ability to coordinate in this fashion without a leader across all the different machines, including across the wide area network. And one of the things that I didn't touch upon in the leader election is the leader election is definitely a big problem, but when you're running across the wide area network, it becomes even worse, because now wide area networks tend to be fairly, the variance is very large. So it's like, okay, are things down, or did my packets just not get there for 30 seconds? In this case, if you're running with a leader situation and your leader's on the wrong side of some kind of network failure, you're faced with a choice of either doing some kind of recovery or waiting to come back. And it's very analogous. Hey.
What do you think of the raft algorithm?
The raft algorithm, right. So the raft algorithm is great. It's also based on paxos. It's a great addition to the field of computer science. I've written a raft algorithm myself. It's easier than paxos, not trivial. There's a lot of edge cases. And most importantly, unfortunately, still very much based on leader elections. So by choosing the leader election, you're able to make certain guarantees, and the leader is basically deciding the sequence of events that should happen, usually based on some kind of in-memory queue. Whereas Decomp is coordinating with a distributed algorithm across multiple machines for what this order should be. So as a diagram, looking back at how Non-Stop HBase works, there is essentially this global sequence of operations, and there's a database or a log, and essentially, we can characterize a region server as essentially, a series of points, right? That is what a region server is, and at any specific point in time, you can read them all together and see what your results will be. So what happens is that the HBase client will normally talk to the HRegion server, and this is where we sort of like intercept and grab things or plug in. And then working with Decomp, we sort of figure out where in the next chain of events are things going to happen, and add an extra operation to the global sequence of operations, the dashed block. Having agreed upon that okay, this is where we lie, the algorithm, the Decomp algorithm has figured it out. Then we're going to apply that operation back down to HRegion. So the operation will actually take effect, data will go into memstore, all that kind of stuff, and become visible to all the other clients as well. And so that's sort of the chain of things. And then then we reply back to the original client saying, hey, not only did we store your data, we stored everything. That's great. So regions are now being replicated multiple times. Put the star next to 3 because, like I said, we can go with 3, but maybe 5 or 7. Any number of sort of replicas, odd, ideal, works. So you can run a bunch of replicas in one data center and then a bunch of others in a data center. Every replica is equally capable. And one of the interesting things is that now region replica assignment becomes a bit more sticky. We don't really have to reassign during a temporary outage, because when the machine temporarily falls out of order, you just talk to the other replicas, and they can all process things fine. Hey.
So does this, fix the problem of availability? No, you talk about the cap theorem and HBase, following the consistency and audition side of things. One of the things was one of the items you talk about is availability in HBase is not really, so not guaranteed. So what you guys are talking about seems to be that availability is guaranteed. I would say 5 9 or something like that.
Right. So to kind of paraphrase the question, does this kind of solve the availability out of sort of cap theorem style? There's no kind of like magical, there's no magical out to the cap theorem. This definitely does a really great job. We do provide strong consistency in the sense that every single machine sees the same order of operations everywhere, but also more thoroughly addresses the availability side of things, because cap theorem is like a 3-way trade-off, and it's not like you can just throw everything out. In this case, we're achieving some measure of consistency, availability, and of course we're tolerant to partitions. Now there's no really sort of free lunch, and the number of machines that you can lose before you start losing access to data is not, there's a number there. It's with 3 replicas, if you lose more than 1 machine, you can no longer make progress. So that's sort of the flip side of it, is that you can't unlimitedly make progress. On the flip side of it is there's no system that isn't like that either. Every system eventually, once you lose enough nodes, you can't make any progress anymore. So it's just sort of that simple. So wall splitting, okay, well that's gone. So we have totally don't use wall splitting anymore. We don't actually even use the HBase write-ahead log because Decomp is providing this for us. As remember what Decomp's job is, if I go back here, is to establish this global sequence of operations. So it's keeping track of what should happen and when, in which order specifically. So it's able to provide to us the order of things that happen, and we no longer need the write-ahead log. Decomp has its own database and log on local disk, and on the downside, you have to store stuff on local disk. On the plus side, now we can leverage SSDs a lot easier. One of the challenges of leveraging SSDs through Hadoop and HDFS is there's just a lot of layers of kind of like software to kind of get to, and SSDs work very, very fast, and sometimes Hadoop doesn't. So,
What happens if the Decomp database goes down?
what happens if the Decomp what?
Database goes down.
Well, the Decomp database is just like a series of local files. But if there is a problem and it goes down, we have the other replicas to take over. This is sort of the definition of a distributed reliable system, is that if any node fails for any reason whatsoever, files get bad, become corrupted, there's other replicas elsewhere, and we don't need to do that.
It's stored on local disk, not HDFS.
It's stored on local disk, yeah, that's right, not HDFS.
So you
And-
make copies of this on different nodes.
Yeah, every node has their own copy of this data, and that's sort of like how things are being done. So there's still sort of like we're still going to pay 3 times data to be stored on 3 different nodes, but instead of all the data being through HDFS, the temporary or the short-term log data is being stored on local disk, and then we're able to flush and push stuff off onto HDFS as normal. So when we are in a situation where you can take down Non-Stop HBase, uninstall it, and bring back up stock HBase as well, so we can have a forward and backwards compatibility story. One of the other things we spent a lot of time on is all the kind of master changes we would have to make. So we wrote a new one from first principles instead. Sounds kind of crazy, and I had a couple staffers who didn't think it was an awesome idea until they realized that there's only 9,000 lines of actual code, and most of it we've just sort of changed the nature of how HBase works. So without wall recovery, the whole wall recovery mechanism is not necessary for us. Without the recovery and the workflow mechanisms, the way that we handle workflow and we assign regions is all very different. So we needed a new HBase. And data storage and replication is again being handled by Decomp. So the master is being replicated itself as multi-master. The regions are being multi-master, so the full system is being multi-mastered, and there's no particular single point of failure. The generalized principle of this approach is called a replicated state machine. And so fairly, Leslie Lamport, who wrote the Paxos paper, kind of strictly advocated that this is the only way to make a reliable system. And sort of in brief, since y'all look like maybe you know how to program a bit, in brief, essentially, a state machine is a state machine. It's kind of like a bad description of it. So you have a state machine, and you have one on every single machine, and if you feed it the same order of operations in every machine, they will come to the same result. So if you have a system, the system we call Decomp underneath, that makes sure that everyone processes things in the same order, then they all become identical the same. So that's how we've rebuilt master. It is purpose-built and extensible, and importantly, this is one of our targets of future open sourcing. So the master is just sort of a pretty cool and a new way. I know the HBase master has kind of a storied history, and people are kind of not super duper happy with it, but also not wanting to kind of upset the apple cart. Otherwise, you're gonna have the last person to touch it owns it, so you don't want to be that person. So you're not really seeing that kind of stuff out of there. But wait, there's more. One of the things we've been putting together and playing with is a JavaScript shell, most importantly for remote execution of code. In this case, we can debug the internals of our servers without having to actually run a debugger. This kind of makes a good kind of operational or in-situ kind of like debuggability, extensibility. Also, I just like JavaScript over Ruby, for reasons. And also, JavaScript is trivially interops with Java. So this is really great. And this is another one of our open source targets of things we'd like to sort of contribute back once we've baked it in fully and other people seem interested in this kind of stuff. These changes can be pretty big, and I don't really want to shove a multi-100 kilobyte patch down someone's unwilling throat. So it's like, hey, wouldn't you mind this kind of thing? And Zookeeper, yes. So what about Zookeeper? Well, the good news is it's left the cavernous building. Coordination and replicated state machine is a very powerful building block, and a lot of the reasons for Zookeeper was to store data in a replicated fashion so that during master failure or failover, you wouldn't lose it. And the RSM approach is quite a bit more powerful. And Decomp provides us all these sorts of operations and process. Now, on the plus side, this should mean that Non-Stop HBase should have a developer mode that will survive a laptop sleep and restart. If any of you have experienced that particular roadblock, as well as just sort of like less moving parts, less daemons, just less stuff. Probably, though, you won't be able to get rid of Zookeeper in your stack because a lot of other Hadoop systems depend on it. However, not having us depend on it will also reduce kind of the footprint of Zookeeper and make it easier to manage. One of the challenges with HBase and Zookeeper right now is if you lose all your Zookeeper data, restarting HBase, it's no longer super duper trivial. So kind of the upshot of all this stuff, so there's a whole bunch of sort of technical pieces kind of like putting together. One of the big things is moving away from disaster recovery and moving towards business continuity. I know a couple of you are really interested in business continuity, making sure your system stays up even during hopefully any kind of conceivable failure. No really failure recovery, just continuous operation. When a machine fails, it comes back, it has a localized recovery, but once it's done its thing in isolation, it can rejoin the world and operate with everyone else. In the meantime, clients will have noticed that this machine has failed and continued on with another machine that hasn't failed. Clients can choose which replica they can talk to, and there's actually a lot of interesting implications in here. Multiple dispatch RPC, I don't know if anyone's seen any of the Google talks, but the idea is that you have two machines. You could talk to one, you could talk to the other. One is slow, one is fast. You don't really know which one is slow and fast. Why not just talk to both of them? You can reduce overall latency at an increase of system resources used. This is all now possible because we have multiple replicas to actually talk to. If you don't have more than one replica, this approach doesn't make sense. We can do this now. And really sort of pushing HBase behind websites is now sort of like, you really should put safely in reach here. Because I know some people do this stuff, and if you look at what Facebook has done, they've added, application server layer cache, multiple clusters. They've really extended it out with a lot of their own custom code. And in theory, HBase is supposed to be providing this kind of fault-tolerant resiliency so that you don't have to. And it does to some extent, but that extent is usually measured in minutes or longer, not in seconds. So this is sort of where we walk in, is NonStop or Apache HBase sort of walks in and conclusively kind of solves this problem. Hopefully once and for all. Once and for all. So that's sort of my rundown of our product. Super Tech, I want to kind of take Q&A for as long as people have questions. We can talk about answers and stuff. You are...
Yeah, I'm wondering what the kind of write throughput penalty is on coordination over like a LAN or a WAN scenario.
Yeah, write throughput penalty. Good question. There's... I wish I could start the project as get rid of the speed of light as a limitation, because until you really think about it, it's actually we're talking about speed of light problem here.
So you consider it kind of safe once they have it in the store on each replica?
Well, actually, Decomp considers it safe once it's written to its own database. Once they've gotten that, but to answer your question, the number we quote is usually in terms of round trips because it depends heavily, but an agreement takes 2.5 round trips to fully complete and everything. This is, the fact is there's really no magic or free lunch. So it's super tricky in terms of performance. We're looking at both, making sure there's a latency performance as well as overall throughput performance. So batching and other things like that, and clever internal software things should keep the overall latency to a fairly low. And then, of course, your own particular latency penalty depends on what your round trip is. So if you're talking from, New York to Singapore, that is like a solid 200 milliseconds or more. Whereas if you're just talking from, from this data center to somewhere on the East Coast, that's going to be quite a bit less, and therefore it's going to, the latency is going to be quite a bit lower. And then throughput is dependent on how much available bandwidth and all that kind of stuff. So,
are you guys using coprocessors to intercept the code?
We are not using coprocessors to intercept this stuff. Our goal here is to sort of provide I kind of use the word plugin loosely in the sense I'm not using the existing plugin APIs. However, we're using a lot of the extensibility that HBase has built into it. The nice thing about not using a coprocessor API is that we retain the coprocessor APIs for our customers to use. So if you have coprocessors, depending on what your coprocessor does, it should actually work without modification. Things get a little tricky when you have indeterminism in your coprocessor, and your coprocessor is the result of it is sort of based on something semi-random, like the time or whatever. That's when we'll have to have an alternate API, but that's just how it goes. So yeah, coprocessors and go. All right, anyone else for Keith? I know Sabash is dying to ask another question. He's got a ton of them in his back pocket.
Doesn't it? Yeah. So it kind of seems like there's a lot of more information passing through the network. Does it seem like there is more, handshaking going on because you coordinate across the LAN, talking to people, talking across? Is that,
Right. Like it's the information count going up or how much data you have to send. Definitely, yeah. There's a lot of tricks that have to be done that can and are being done. Like for example, and a lot of these things have been pioneered in the pioneered by the subversion guys. They've been doing this for a long time, and they, like for example, in their case, they like a subversion commit might be really large, right? Hundreds of kilobytes. Sending that 2.5 times across the network is definitively a no-go, and they don't do that. What they do is they send the data the minimal amount of times, and they have a bunch of much smaller metadata that they sort of exchange, and they can still come to the agreement and get the data across without having to send a very large blob across the data center links multiple times. So all that stuff is available, and we're leveraging all of that, all those techniques. That's one of the nice things about working with these guys that they've been working on Decomp and having it in field operations for years now. So we're able to leverage all that kind of experience, and as well as bring our experience of running HBase and developing HBase to them as well. So it's going to be pretty crazy soon enough here. As you can imagine, HBase is a little bit higher volume than Subversion. I think the operation every minute is kind of average. So they do the Hadoop product does a lot more ops a second. Obviously, Hadoop is a very, very, very busy file system, and so they're being super successful there, and that's great too. So I should probably talk about our NonStop Hadoop product a little bit as well. Essentially, fairly similar. The big difference is that the metadata of Hadoop is what's being replicated. In our case, all the data of HBase is what's being coordinated and replicated. In the NonStop Hadoop case, what's happening is that the name node metadata, what file is where, the existence of files, all that stuff is being replicated not just across multiple name nodes, but also across the wide area network to name nodes on the other side. So you'll have some name nodes here and some data nodes here, some name nodes and data nodes over there. No diagram for this in this case, sorry. And essentially you have two clusters that operate together. And they're actually not really two clusters, they're a single cluster, so they share the exact same tree. And what happens is you write files and complete files on one side of a land link. These blocks are then replicated and copied to the other side. So everything is being replicated back and forth. There's even options to kind of limit the replication so that you don't have to replicate everything across multiple data centers. You can run in a giant kind of, have one giant file system a la AFS, but only have data in certain countries or in certain data centers and not having to copy it everywhere. So they do all these sorts of things as well. So it's pretty cool. So we will be leveraging and working with them as well as doing our own coordination with HBase of our own operations. So, and one of the things that took me a long time when I started at WANDisco was sort of coming to understand this word coordination, and it makes a lot more sense if you sort of look at the replicated state machine concept, where basically each replica is essentially, each HBase replica is, all its edits haven't been done in order from the very, very start to current time now. So if everyone agrees on the order of operations, including compare and set operations and many other compare and delete operations, all the other atomic operations that HBase does, if everyone agrees on the order of these operations, does them in orders, you don't need a global lock for everyone to agree upon it, converge, and end up having the exact same. Our PhD guys use the word convergence, but essentially every replica becomes literally a replica of every other one. So it's taken a long time to kind of wrap my head around this idea of coordination as a super powerful sort of metaphor, and a super powerful approach to it. And you can definitely use coordination in a lot of other ways. If you look at the Raft paper, which Subhash mentioned, the Raft paper also talks about replicated state machines, and it's kind of a staple in distributed systems research. So, as far as I'm aware, we'll probably be one of the few Paxos-enabled databases that works over the LAN. I know there's a couple of them, but it's not. Most of them are doing cool, not open source stuff, so I'm not 100% sure what they're all doing. So, cool. Any other questions? I know it's a lot of info to take in.
Maybe it's not so much related to its non-stop HBase, but it's curious about Facebook's take on HBase. They've forked off the original HBase and they're currently, now they have HBase. Is it?
Yeah, what is Facebook doing with HBase? That's a good question. Talk to some of the guys. They've spent a bunch of time on this thing called HydraBase, which people have probably seen, and this is their Raft implementation. They claim that they run it. I'm sure they do. I think the key thing for them is that they aren't running it in full production. They're running it in shadow production mode, where it runs in parallel with everything else, but actually doesn't answer real-time queries. So it's there. It runs in production. The big problem, of course, is that they've written this thing. They're trying to contribute it back, but now there's a large integration task, as well as just the task of sort of making it solid and sort of operational for everyone. And can you run this stuff on your own? So it's pretty tricky. I've also heard that Facebook has spent a bunch of time on C++ databases, RocksDB, people have probably heard of. So I'm not really sure what they're up to. It's a pretty big company, so I think the answer is they're up to everything. It's like, oh, why have one database when you have 6? Why not? Just a couple developers. So I'm not really sure. They're probably not going to back off of HBase because they would have to port the entire Facebook messages backend off of it, which seems like probably take a while. So. All right, so conclude. Oh, cool. Blue shirt guy.
No basic question.
Yeah.
The non-stop plugin.
Yeah.
Is there some easy way to tell when you're running without it and it's got some bad, and then you plug it in and it doesn't do good? In other words, in the past, mostly the basis they talk about TPC or performance or memory size or something, and so it's easy to figure out whether to modify it or not.
Right.
Besides just, what is your, what's the reason to plug it in?
Yeah, absolutely. It's why would you use NonStop? what would you notice that's different? Obviously, we're, apart from cosmetic things like, well, geez, this status page looks a bit different, kind of stuff. Practically speaking, one of the big things is availability. You can, nodes can fail without, having, a larger unavailability event. And secondly, besides just availability, it's also feature enablement. Such a wacky word, but essentially you can now start to do things that you just couldn't do before, like running HBase across multiple data centers. That's something that just currently really can't do today. So this is all about sort of like taking what's there and making it extend to more operations, making it do more complicated and more challenging operational modes. I think the trajectory of sort of like operations and systems has been that first people had a rack, then people had a bunch of racks, and then they had a data center, then they had EC2, and all of a sudden they had to jump in this world. They needed to have multiple data centers, and people have been putting systems together of various sorts to kind of handle the multiple data center case, and it's been tricky to do it in a principled way. And some systems like HBase just don't really, just doesn't have your back. I feel. You want to run across multiple data centers, and if you're doing something where just because the data center went down, and EC2 goes down infrequently, like every other year, I guess, but every now and again you got that US East is down, for like a solid 10 hours or whatever. I guess in the hindsight, Amazon moved their data centers to the East Coast because of earthquakes in Seattle, but there's been way more hurricanes taking out data centers on the East Coast than there's been earthquakes in Seattle taking out data centers. So I guess that's where everyone lives. You got to be geographically local, and that's actually, I guess, the other flip side of it is that being able to serve writes out of a geographically localized way is basically like one of the killer features that people must have. For people who have to have it but don't have this kind of stuff backing them up, they baling wire, gum, tape, just kind of make something work. Usually the cost of that is that they're harder to maintain. Your staff tends to be, you tend to have that one lynch person, the one smart DevOps guy who just makes it work somehow magically and no one else can figure it out. And so I've seen that happen a lot, many times over. And hopefully we can start solving that definitively. On the downside, it's not open source, but on the plus side, it actually exists, which is kind of a big deal. So.
Do you guys have any plans to open source and do like a commercial support model like Workforce or anything?
Yeah, open source commercial support model. Not that I know of. I don't. There's essentially three parts to Non-Stop HBase. There's Non-Stop for HBase. There's HBase, all the stuff that brings. There's Decomp and all the algorithms that embody it and that brings. And then there's also a bridge layer in the middle here. And there's a bunch of plans that we want to open source some of this stuff. One of the things we want to open source is master changes. The JavaScript thing makes me happy, but I'm sure no one else cares. But master changes are a big deal. Moving the master to a more principled, more just a better, easier maintainable, I think everyone would be super happy about. Because that master it's pretty crazy to change. So, stuff. Cool. Anyone else? I mean, I'll stick around for a bit if you want to ask me super pointed questions here. You want to make me look bad or whatever. All right, thanks for coming, guys. Sebastian, do you want to say anything trailing out? Are we?
I mean, if you guys want to stick around for the tour,
Data center tour afterwards, if you want to see, if you want to lose, your hearing or whatever, bring some earplugs, I guess. Is it still really noisy in the data centers? Josh, are data centers still stupidly noisy?
It's still really noisy.
Yeah.
Not the one in here.
Oh, they're awesome, so not theirs.
Some people have, really high-dense servers, but in here they haven't really loaded up too much yet, so it's still relatively quiet.
So they took all those gamer fans, they're nice and quiet, and moved them into the data center, and that's what they did.
It's still water. Yeah, it's already used to.
Cool. All right, guys, thanks. Yeah, thanks.